So I'm going to tell you a little more about the basics of finite type invariance today. But before that, so a word about homework. So I thought about homework too. So you know, it looked like a cool idea to ask you to well, completely open-ended question, and maybe it was a cool idea. My expectation, so the question was why not Z mod, or why Z mod 3? And the correct answer is, or I don't know what's the correct answer, that's kind of the problem. There isn't a, I mean, okay, it doesn't have to be Z mod 3. There are lots of alternatives. There are and you start, you know, first you generalize to Zn, then you generalize further and think, actually, why not any group? And then you continue, not necessarily a billion, but then you have to think about it more. Then you continue, actually, it's enough to look at a conjugacy class in a group. Actually, you continue, well, maybe it doesn't even have to be a group, and there are examples where that come from non-groups, and then you can, and basically it goes on and on. And my hope was to see how far you will go, and but it was in a sense unfair, because different people have different background. So some people immediately knew that the meaning of my question was why not more? And other people gave reasonable reasons why it should only be 3, because of course to go beyond 3 you need to make some change. Okay? So, so I decided not to mark the homework, but instead at some point in the future I hope to give a class generalizing it step by step until we get to like extreme generalizations. Okay, homework 3 is due at midnight. Extensions will be considered, so if you are in trouble, let me know. Homework 4 will be on the web soon, and let me remind you that we've defined a finite type invariant, so, and let me also remind you and also add to the definition. So I will let V sub m, calligraphic V sub m, be the class of all, the set of all finite type invariants of type m. So an invariant V belongs to V sub m means that its m plus first derivative is equal to 0, which is the same as saying that if you evaluate it on a knot with more than m double points, you always get 0. And maybe I'll add a tiny bit of comment here. So first of all, this space of invariants of type m is clearly a vector space. Or in fact, if we're looking at invariants, this is if we're looking at invariants with values a field. If you're looking at invariants with values in a group, it will be a Z module. Okay, the sum of two invariants is again invariant, and if you multiply an invariant by a scalar, an integer, it is still an invariant. So first of all, it's a vector space or Z module. And second, just to be clear about my definition, if you are of type 7, you are also of type 8. Okay? So if your 8th derivative vanishes, your 9th derivative also vanishes. So in other words, V sub m contains V sub m minus 1. Right? So anything of type m minus 1 is also of type m. Okay, it's not a direct. Okay, the type of an invariant is not a unique number, right? Because there is a minimal type, but for each invariant, but there could be, but it's also of any other type. Okay, good. So I promised that we will start to classify. We will try to classify finite type invariants, and the idea is to continue borrowing from polynomials. So, so if a polynomial is sorry, if the m plus first derivative is equal to 0, so if we know that Vm plus 1 is equal to 0, then it implies that V up m is constant. I don't know yet what constant means, but I will know in a minute. But anyway, the idea is that classifying constants is easier than classifying functions. So we will try to classify those constants. Okay? So what does it mean that it's a constant? It means the following. I want to say that it is independent of the embedding into the ambient space. The ambient space, I just mean R3, the space in which all of this is happening. So let me explain. So you see, what I want to assert is that suppose V, so in other words, suppose V is of type M, then it means that I claim that it means that if you evaluate V on a node that has precisely M double points, then the output no longer depends on the topology. Namely, if there is somewhere an additional crossing and you switch its sense, so you take that additional crossing and you replace it from an overcrossing to an undercrossing, I claim that you don't get any, that the answer does not change. Why? Because by definition, over minus under is V evaluated on, well, the M crossings remain the same, that over minus under is the definition of a double point, so that's V evaluated on a double point, but now we have more than M double points, so by definition, this is equal to 0. Okay? So therefore, this is equal to that. The invariant V evaluated on M double point does not change if we switch a crossing. So what remains? Okay? So what, or let's say it differently. What is the space? So what remains is a functional. So V is now a functional on the space of M singular nodes, or more precisely, V up M is a functional on the space of M singular nodes, modulo over is equal to under, with values in our group. But what is this quotient? So what remains if what remains of an M singular node if you are allowing to flip over crossings to under crossings? So the answer is that something does remain. Namely, so let me draw an M singular knot. Here is a 2 singular knot. Okay? Now, suppose you are a green ant walking on the knot. Okay? So you walk on the knot and you, so let the knot, remember that the knot is oriented, so you walk in the direction of the orientation. Okay? So you walk and you mark what you see. So you say, I went through a double point. And then, and you actually, you know, you leave a stone behind to remember that you've been through that double point. And you mark it 1. And then you go and you pass through that double point again. So you say to yourself, I'm again through 1. I went through 1 and then again through 1. Then you continue walking and you walk through a fresh double point and you call it 2. So again, you mark to yourself, I went through 2, and then you continue walking, and then you come through 2. You go through 2 again. So you mark it, and then you come back to the beginning point. However, if the knot with double points was different, so if it was, say, this one. Here are the 2 double points, so M is equal to 2 for the sake of the example. Then, again, I'm a green ant and I'm starting to walk here. Okay? Then I go through the double point, I mark it, I went through 1. Then I keep going, I go through the second double point, not through the first one once again. So I go through 2. And then I continue walking, I walk through 1 again. And then I continue walking and I walk through 2 again. Sorry, how did it go? I start here. 1, 2, sorry. 1, 2, 1 again, 2 again, and only then I come back to the beginning. And that's a different sequence. Now this sequence is determined up to cyclic permutations, because the starting point was not canonically defined, and up to renaming the points. So, I mean, there was no particular reason to call this crossing 1 and this one 2. They could have been named the other way. Okay? So, the sequence is not quite unique, but still, these 2 are different. So, one good way to indicate such a sequence is to write a circle. The circle stands for the parameter space of the knot. Right? This circle is the circle that parameterizes the knot. So the ant starts here, then it goes through 1 and through 1 at some point later, and through 2 and through 2 at some point later. And what I do to indicate that this one is the same as that one is I connect them with a chord, and I connect the 2 with it, the two 2's with a chord, and I've done something silly. I've drawn the chord. I've drawn the chord diagram of this knot. Sorry. So I go through. Sorry, the order by which I go through things is 1, 1, 2, 2. So I have a chord connecting this one with this one, and this 2 with this 2. Okay? And similarly, for this one, I will draw a chord, a chord diagram, and draw chords connecting. So this is the starting point. So I go from, I have a chord connecting 1 to the other one, which is diametrically opposite, and the 2 to the other 2, which is diametrically opposite. And these 2 chord diagrams are different. Now, you know, a different way to say, you know, if I wanted to say it more quickly, I would simply say that the chord diagram is the parameter space of the knot, which is a circle, and I connect by a chord any pair of points which are identified in the image. So if you think, so if you have like a knot is a map from a circle to R3, and these 2 points map to the same point in R3, and these 2 points map to the same point in R3. Likewise here. Okay? Now, the chord diagram comes, well, since I can cyclically permute so I can choose the start point to be anything, the start point is not marked on the chord diagram. And since I could rename the crossings, the double points, the numbers are also not a part of the diagram. So these 1s and 2s should not be marked. But still, even without the markings, these two are different chord diagrams. Okay? So no sequence of, so no amount of, okay, sorry, I should have said, if you flip an overcrossing to an undercrossing, it does not change the chord diagram. Flipping an overcrossing to an undercrossing happens elsewhere in the knot, not in the vicinity of the double points. Okay? So, so no amount of flipping of overcrossings and undercrossings is going to take you from this knot to that knot. At most, you will go from this one to, like, you can flip this crossing, or you can create another crossing between here and here by pulling these things on top of each other. But the double points don't change when you when you flip crossings. So I'll give these things names. So such a thing is called an M chord diagram, and we found that right, we found that every M singular knot has an underlying M chord diagram. Okay? So, the other point is that every M chord diagram corresponds to an M singular knot. So, you know, if you draw an M chord diagram with a large value of M, clearly you can turn it into an M singular knot, right? All you have to do is, well, you start walking in R3, and whenever you pass through a point that is at the end of a chord, you mark it, and then you just continue traveling randomly. And then when you pass through the other end of it, when your parametrization passes through the other end of a chord, you just make sure that you come back to where you've been and cross it and go through that point once again. And R3 is a big space. You can easily arrange that to do that, okay? So clearly, there is also a map from M chord diagrams into M singular knots modulo over is equal to under. By the way, if I wanted, I could make it completely explicit. So here is a different way to associate a knot with double points to an M chord diagram. So basically what you do is, the problem is that I don't have a good eraser. I only have a stroke eraser. So let me try to do it nevertheless. So, sorry, and I wanted it blue. I'll do it this way. So 1, 2, 3, 4, 5, 6, 7, 8. And now I need to make a chord between this and this, right? There is a chord here, so I need to make a chord between here and here. I'll go push push a finger. So I'll draw in R3 well, okay, I'm just drawing a picture in R3 that clearly has the same chord diagram as the one I was hoping to get. Likewise here. And so on. Okay? So I leave it to you to prove that I'm sorry, I'm really not fully here today. So, you know, what I've done is I've constructed a map from M singular naught modulo this relation into M chord diagrams, and I have shown to you that this map is surjective. Every M chord diagram is the chord diagram of M singular naught, of some M singular naught. You still have to show that it is injective. Namely, that if two M singular naughts have the same M chord diagram, then you can get from one to the other by a sequence of crossing changes. So this will be a relatively easy assignment, exercise in today's assignment. Okay? But anyway, the conclusion is that the conclusion is that V up M is really a map from M chord diagrams into our A. Okay? So, two things. First of all, I want to several things. First of all, I want to give it a name. So, the standard name is to call it W sub V. So, the W of V, and it's the so-called the weight system of V. So the mth derivative is the so-called weight system of V. Second, with slight abuse of language, I will replace this space by, so I will allow you to take formal linear combinations. So I will define a space D sub M. So D sub M will be the space of formal linear combinations of M chord diagrams with coefficients in A. So you should think of it as, like, if A is a field, you should think of it as the vector space with basis elements, one for each chord diagram. Or, so in other words, I will allow you to also look at combinations like 7 times this chord diagram minus 3 times this chord diagram. And of course I can extend WV to linear combinations simply by linearity. So, so W sub V is now a map from dm into A. And already we have a corollary. So corollary, there are only finitely many invariants of type M for each M. So there are only a finite number, no, sorry, not a finite number, okay. I mean, if I wanted, sorry, it's really a finite dimensional space of. So really I should be saying it differently. So V sub M, well, I already mentioned that it's an A module, and I want to say that it is an A module of finite rank. But really, it means that up to linear combinations, there are only finitely many invariants of type M. So proof,
hello.
Yeah.
Sorry, what is V sub M?
The set of all finite type invariants of type up to M, of type M. Okay? So, proof, the space WM, sorry, V sub M maps into DM dual, right? Because this is the map W. This is the map which maps an invariant into its weight system, right? Now, this space, well, the space DM itself is finite rank because there are only finitely many M chord diagrams for each M. I mean, so this is clearly of finite rank. Okay? But what is the kernel of this map? So suppose you have two invariants, V1 and V2, and you know that they map to the same, that they have the same mth derivative. So they map to the same element of dm. So in other words, suppose that I know that W V1 is equal to W V2, right? That's the same as saying that W, or you know, that's the same as saying that the mth derivative of V1 is equal to the mth derivative of V2. And this is the same as saying that that the mth derivative of V1 minus V2, if you look at V1 minus V2, then the mth derivative is equal to 0. But this is the same as saying that V1 minus V2 is actually an invariant of type M minus 1. So the kernel of this map is Vm minus 1. Actually, I don't know why I looked at equality. I mean, the kernel is simply the invariance of type M whose mth derivative is equal to 0. And if an invariant is, has the mth derivative equal to 0, then it means that it's of type M minus 1. Okay? And this one is finite rank by induction. So the proof is by induction, and I'm assuming that I've already shown that this one is of finite rank. I suppose you have to base the induction, and the base of the induction is to show that invariants of type 0 are of finite rank, but it's very easy to check that the set of invariants of type, that an invariant of type 0 is only the constants, right? If an invariant doesn't change at all when you switch crossings, then it's a constant. So so we're done by induction. Okay. But
just
yeah,
clarify.
yeah.
So V0 is the set of invariants on knots with 0 singular points, so just regular knots.
No, no. Vm is the set of invariants of knots with 0. I mean, all VMs are invariants of knots with no singular points, but they have a condition. So Vm vanishes if you extend to knot with m+1 double points.
Okay.
Okay? V0 means that it vanishes if you extend to knots with one singular point. But this really means that V doesn't change if you flip an overcrossing to an undercrossing anywhere. And that means that V is a constant. Okay? So V0 is clearly of finite rank, and therefore by induction, so you know, okay? Okay, notice what I didn't say. So let me put in red what I didn't say. I did not say that this map is onto. I don't need it to be onto. Okay? All I know is that it's onto a submodule of a module of finite rank. Right? It might not be surjective, but its image is a submodule of a module of finite rank. So it is of finite rank. So the image is of finite rank, and if the image is of finite rank and the kernel is of finite rank, then the space itself is of finite rank. Okay. So actually, the next so I've shown that Vm is of finite rank, but I haven't yet given you an algorithm to figure out what is this rank, to determine what is this space. Because in order to determine what is this space, so V up M is going to be, well, you know what, let's work on a field to make life simpler. V up M is going to be the direct sum of this with the image. Okay? But I still don't know what is the image. I only know that it's a subset of something finite. A subspace of something finite. Okay? So I still have to determine the image. And I claim that the image is in fact not everything. There are things that are not in the image. Okay? Rain disappeared all of a sudden. I wonder if it's a technical issue or if he quit. So anyway, why is the image not everything? So I claim that every W, so I claim that W sub V satisfies two relations, at least two relations. So the first relation is easy and sort of wrong, but it's still worth mentioning. So my claim is that if you have a chord diagram that has a so-called isolated chord, so a short chord, okay? A chord that does not intersect, and that sits in the corner and does not intersect any other chord. So all other chords are away from it. So one chord whose endpoints are near each other. Okay? So I claim that W sub V will map such a chord diagram to 0. Okay? So definitely definitely the map I wrote before is not onto, because in DM Joule you could map this to something non-zero. Okay, so that's the meaning of having a relation. So why? The answer, the reason is very simple. I can represent such a diagram by a note that has a kink. So basically, if you look at a note with a kink, so represent this diagram by a note with lots of double points and maybe some honest crossings. Okay, but represent this isolated chord by a kink. Now, when you will resolve this double point, the two resolutions will be this one and that one, and you're going to compute the V up M on the, V on the difference of the two. Right? But these two are the same. So you get 0. Or, more precisely, what I want to say is that V evaluated on this minus V evaluated on that is equal to 0. Okay? So that was cheap, and it's also half wrong, because I think I mentioned that framed knots are always better than unframed knots. And if you look at framed knots, then this turns out to have a different, so at framed knots, this is, well, these two knots have different framings, and so you don't get 0. And in fact, the reason for the name is this relation is called Fi for framing independence. It basically says that you're looking at invariants that don't distinguish different framings. Okay. And then comes the more interesting relation, the so-called 4T relation. And let me explain where it is coming from. So suppose you have the following configuration. So you have a note with a double point marked here, some m-2 double points elsewhere in space, I don't care where, okay? And an additional lasso which lassos around the double points but below it. Okay? And suppose I compute, so suppose I look at the difference between this and the same thing, no, sorry, let me draw it differently. The same thing, but with the lasso going above. So the exact same picture, the other m-2 double points are unchanged, everything is unchanged, except that the lasso switched from going below to going above. Okay? Now, on the one hand, well, I could pull the lasso out, it's completely below. Topologically, this is equivalent to just pulling the lasso out, and then I could push it back in, above. So topologically, the two sides are the same. So if I have a knot invariant V and I evaluate it on here, or on here, the difference is equal to 0. They don't change. Okay? On the other hand, I can get from the left to the right by flipping this crossing, and then flipping this crossing, and then flipping this crossing, and then flipping this crossing. So I could get to it topologically, or I could get to it from left to right by a sequence of 4 flips. Now, each time you flip a crossing from under to over, the difference, the change in the value of V, is V evaluated on a double point. And you're going to have, once you do that, you have the double point where you flip, so it's either here or here or here or here, right? And then so you have one double point, then the double point at the center, which is always there, and then m-2 double points elsewhere in space. So each time you flip, you get V evaluated on on a node with m double points. But a node with but evaluating V on a node with m double points is the same as evaluating its weight system on a chord diagrams with m chords. So we found that the sum of 4 evaluations of W on 4 different, potentially different chord diagrams with m chords, so that sum is equal to 0. Now that's a relation, but let's try to make this relation explicit. So what does the chord diagram of this picture looks like? So, okay, so corresponding to the 4 flips, there will be 4 chord diagrams. And what do they have in common? So all of them have that double point here, which is in the same place. So all of them have one chord which doesn't ever move. Same place. Okay? All of them have an interval. So, I mean, remember the circle in the chord diagram really represents the parameter space. And when you travel through the node, the lasso is always in the same part of the parameter space. So all of these 4 chord diagrams have a little interval marked on the parameter space, and this is the interval which is going to parameterize the lasso. Okay? And then all of these chord diagrams have m-2 chords which are not changed between the 4 pictures, between the 4 flips. Okay? So all of them have m extra chords, maybe this one, m-2 extra chords, maybe this one and that one, and they are positioned in the same way in all 4 pictures. So I suppose I'm doing the case where m is equal to 4. Okay? But what is it that does change? So far all the 4 pictures are the same. But what is it that does change? So the double point could be either here, or here, or here, or here. Right? These double points, so let's look at 1 and 3, say. So for double point, if the double point is at 1, if you're flipping crossing number 1, then you have a double point which stands for a part of the parameter space. So like if I turn this into, sorry, let's make it red. So if I turn this into a double point, then a point from the lasso is identified with a point on the vertical strand. By the way, what is the vertical strand? The vertical strand is one of the sides of these chords, right? So this is the vertical strand, and say this is the horizontal strand. Or the vertical strand is parameterized by a small neighborhood of this end of that chord, and the horizontal strand is parameterized by a small neighborhood of that end of that chord. So, and that's the same everywhere. So this represents the vertical, this represents the horizontal, same. I get an extra double point, which is an extra chord between the lasso and the vertical strand, and it's right before the place where the vertical strand meets the horizontal one. So it's right before, so basically I get an extra chord going from the lasso to the part that parameterizes the vertical strands right before the end of the fixed chord. So this will be, so this is the picture corresponding to double point, to flip number 1. The picture corresponding to flip number 3 will be the same thing, except the chord from the lasso to the vertical strand ends right after the place where right after the double point with the horizontal strand. So basically you'll have a picture like this. And similarly on the other side, you'll have this, and that. Okay? So these are 4 different chord diagrams. But they differ only in sort of basically near in the neighborhood of this vertical strand. Sorry, of this fixed chord. Now, each of these things comes with a sign, right? Because, well, I said you flip from under to over, but each flip is either from a negative crossing to a positive crossing, or from a positive crossing to a negative crossing. And that means there is a sign difference. A double point is positive minus negative, and there will be a sign depending whether you go from positive to negative or from negative to positive. So you have to be careful and check the signs. And I've done it for you, and I'll just simply tell you that the relation is that this minus this is equal to this minus that. Or what I really mean is that if you compute the weight system, if you compute W on this and subtract W computed on that, then it's equal to W computed on this minus W computed on that. And the moral is, so this is an additional relation that W has to satisfy. Okay? And I'm almost running out of time, so I'll have to get back to it next time. But let me just state the main theorem. So this is the so-called, well, the fundamental theorem of finite type invariance. And it says that over Q, this is all. Meaning, if W, which is a linear functional on M chord diagrams, satisfies framing independence and 4T, so the two relations that I've shown, then there exists an invariant V, which is of type M, such that the weight system of that invariant is W. Okay? and we're out of time, so I'll stop here. Questions, comments?
Yeah, so you said we can ask for extension. Can I submit tomorrow?
I'd rather get it by email.
Okay.
Okay. Other questions or comments?
So basically, you can get every single finite type invariant by direct summing there's like type 1 invariant, there's a linking number, right? So then you just take that space and then you direct sum with a bunch of dual spaces of chord diagrams.
Modular relations.
Modular relations, yes.
Yes. Or, you know, I like to think of it that I study invariants day by day. So, on day number 1, I study invariants of type 0 and I only learn about the constants. On day number 2, I study invariants of type 1 and they correspond to chord diagrams of degree 1, with one chord. On day number 3, I studied, let's start with day 0. So on day number 2, I study invariants of type 2, ignoring invariants of type 1. I'm thinking of invariants of type 1 as trivial. Okay? And then they correspond to chord diagrams of type of degree 2, and so on. By the way, maybe I should have phrased it differently. Here's a different phrasing. So Vm modulo Vm minus 1 is isomorphic, so over Q. If you consider type M invariants modulo type M minus 1 invariants, then this is the same as chord diagrams of degree M modulo framing independence and 4T, and take the dual. So in other words, look at linear functionals on chord diagrams of degree M which satisfy framing independence and 4T. The dual of that is the invariants that I want to study today modulo the ones that I already understand. Modulo the ones that I studied yesterday. Okay?
Wait, how does this change when you change the ring from Q to something else? I'm not clear on what.
Oh, so this is over Q. Over anything of characteristic 0, it's the same.
Okay, right. Yeah, that makes sense.
And over Z, it's an open problem.
Oh.
So the answer to your question is how does it change? Of how does it change is I don't know. It's kind of ridiculous that something like that, so basic, would be open over positive character, or over Z mod 2, but it's open over Z mod 2 even.
Sorry, what is the framing independence again?
Framing independence is the relation, written here. So if you have an isolated chord, the diagram maps to 0. Okay, sorry if today was a bit disorganized and sort of slow pace. I'm not fully here today, I'm sorry. Anyway, see you on Friday. I'm turning off the video.